Today we are looking at separation of variables, a method used to solve certain partial differential equations. We begin by assuming the solution has a special form. We write u of x and t equals x of x times t of t. Here, x of x is a function of x alone, and t of t is a function of t alone. This assumption lets us split the problem into two simpler pieces. Next, we substitute this form into the partial differential equation. After substituting, we divide through so that every term involving x ends up on one side and every term involving t ends up on the other side. Now we have a function of x alone equal to a function of t alone, and this must hold true for every value of x and every value of t. The only way a function of x alone can always equal a function of t alone, no matter what x and t are, is if both sides are equal to one fixed constant. We usually call this constant minus mu squared. This single fact is what allows us to break the partial differential equation into two separate ordinary differential equations, one in x and one in t. For the heat equation specifically, this gives us two equations. The first is x double prime plus mu squared x equals 0. The second is t prime plus alpha mu squared t equals 0. Now we bring in the boundary conditions. It is very important to know that boundary conditions are always applied to x, never directly to u. Here is why. Consider u of 0 and t. By our assumed form, this equals x of 0 times t of t. If the boundary condition tells us this must equal 0 for every value of t, then, since t of t is not always 0, it forces x of 0 to equal 0. So the boundary condition transfers directly onto x, giving us a condition purely in terms of x. Let us check this logic with a simple analogy. Imagine a function that depends only on x and another function that depends only on t. If these two functions are equal to each other for every possible x and every possible t, then neither function can actually be changing at all. That means both functions must secretly be the same fixed constant value. This confirms why splitting the partial differential equation into two ordinary differential equations, connected only by a shared constant, is the correct and valid approach.